Okay, so yeah, I'm going to talk about pseudorandom correlation functions from variable density LPN. It's a joint work with, so I led Boyle, Niv Gilboa, Yuval Ishai, Lisa Cole, and Peter Scholl. And during the talk, please, I don't know how you usually proceed here, but I'm really fine with taking questions on the fly, especially since the talk's probably way too long anyway, so I prefer to spend more time explaining some things and then skipping others. So what's the question we're tackling here? The high level thing we care about is this general question of how to use correlated randomness to help cryptographic protocols. So it's well known that if you have access to a source of secret correlated randomness, then you can do cryptography, and you can even enable very efficient information theoretic cryptographic protocols. So the two most perhaps famous examples are, first, if you have access to, say, the equality correlation. So both Alice and Bob get random strings which satisfy the simplest possible correlation, which is that they are equal. Then you can do perfect communication, that's just a one-time pad. On the other hand, if you have access to a slightly more complex kind of correlation, you can do the GMW protocol. So when I say slightly more complex, what I mean is the Oblivious transfer correlation, where, say, Alice and Bob gets long strings RA as SA and RB as B, such that the bitwise XOR of RA and SA is the bitwise AND, sorry, of RA and RB is a bitwise AND of SA and SB. So some things that satisfy some degree 2 correlation, if you view that as a multivariate polynomial over F2. And so we know that if we have access to random strings that satisfy these correlations, then we can do information theoretic secure computation of arbitrary functions. So that's a celebrated GMW protocol. So the starting equation of all this line of work is, okay, what can do better? What can we improve here if we switch to the computational setting? And in particular, is it possible to compress this correlated randomness? Because, well, the amount of correlated randomness you need in the information theoretic setting is typically very high. So for perfect communication, you need as much as the message you transmit. That's a very famous result of Shannon. And for the GMW protocol, you need as much correlated randomness as the size of the circuits which you want to securely compute. So could we compress this correlated randomness if we have access to computation? Well, for perfect communication, it's easy. It's just a notion of a pseudorandom generator. A pseudorandom generator is essentially a tool that allows to compress the equality correlation, and you computationally preserve the security guarantee that everything looks random. And at the same time, you maintain this correlation when you stretch the seeds. And that's what's used to create stream ciphers. So a way to formulate what we want would be to have a more powerful notion of pseudorandom correlation generators, which will be a mechanism that generates correlated seeds, so a seed for Alice and a seed for Bob, such that these seeds can be expanded into long pseudorandom instances only via local computation. So Alice expands her seed locally, Bob expands his seed locally, and the output should look like long pseudorandom correlated seeds, like many instances of random oblivious transfer. So slightly more formally, a pseudorandom correlation generator, that's a pair of algorithms, a generation algorithm and expand algorithm. The generation algorithm generates a pair of correlated seeds, and the expand algorithm expands a seed for each party into a long pseudorandom string. And we want two properties. The first is that if you expand the two seeds, what you really looks like a random instance from the target correlation. But the second and most important property here is that you even want security against an internal adversary, in the sense that it should be, for example, that if you expand the seed of Alice, then from the viewpoint of Bob, this looks like Alice has just sampled a random string, conditioned and satisfying the correlation with the string that Bob can compute from his own seed. And we want, of course, the converse property in the other direction. So why do we care? What would be so nice if we could have access to such a pseudorandom correlation generator? One of the main motivation is to be able to do what we call secure computation with silent preprocessing. So what do I mean by silent preprocessing? So in secure computation, we often divide the protocol into two phases: the preprocessing phase, which is independent of the target function, and the online phase, which depends on the target, which is independent of the target inputs, of the inputs of the parties. And then the online phase, which is allowed to depend on the inputs of the parties and which we want to be very efficient. Here we further divide the preprocessing phase into two subphases. The first one is a one-time, very short interaction between Alice and Bob, during which I will use a distributed protocol to interactively generate the two seeds. So this protocol is interactive, can use some heavy computation, but the important feature is that the total amount of computation and communication is essentially independent of the amount of correlated randomness which they plan to have later on. So after this one-time short interaction, Alice and Bob can store a small seed. You can view it as exchanging a business card for secure computation. We might do secure computation in the future. We have a short interaction. I give you my business cards, and this will allow us later to do secure computation efficiently. So later, when Alice and Bob discover that they might want to securely compute the function, then the silent phase comes up, where Alice and Bob perform the heavy bulk of the computation, which is converting their small seeds into the amount of correlated randomness which they will need in the online phase. And so this can be computationally more heavy, but it does not require any interaction between the parties, no communication. And finally, there is a usual online phase, which we want to be non-cryptographic, so only involving very simple, lightweight operations and not heavy cryptographic computation. Do you see the bar in the middle, like with my mails and everything? Is it hiding the lower part of the screen, or is it just for me?
We don't see it. We see the slide.
Oh, okay, good, very good.
So, question: what you mean here is that the length of the one-time short interaction that has no asymptotic dependence on the circuit or function that you want to compute. It's just security parameter dependence.
Yeah, so in practice, it will have some logarithmic term, but you could always upper bound the log of the circuit size by, say, the security parameter if you want to deal with all polysized circuits. Okay. So in practice, we just settle for something which is, say, polylog in the circuit size.
Okay, thanks.
Okay, so that's the goal. What's known about that? So we can essentially categorize what exists in terms of whether it's only a feasibility result or it truly gives something efficient that you could use, and whether it targets very wide class of correlation or much more restricted correlations. So typically, we've known for a long time that you can compress so-called linear correlations, assuming any one-way function. So in the two-party settings, that's just the equality correlation, you just need a PRG. In the multi-party settings, that was done by Gilboa and Ishai in 1999. And we've also known for a few years now that if you want to compress extremely complex correlation, well, you can always tackle this problem with a heavy hammer. So you can compress all correlations from IO or all additive correlations where the parties get additive shares of some things that satisfy some correlation defined by some polysize circuit from LWE, like using things like multi-key FHE and the like. So when we started working on that, we initially developed techniques to achieve much more efficient kind of constructions for specific correlations that were of interest for secure computation. So specifically, we've looked mainly at the Oblivious transfer correlation that I mentioned, as well as its generalization over large field. So the OLE correlation and the simpler variant vector OLE correlation, where you fix one of the inputs to be always the same. And so there are a bunch now of constructions. One of them I'm going to present in this talk that require the learning parity with noise assumption. I'll also give more details along the way. And that can achieve pretty great efficiency, actually. And for so this vector OLE correlation, this OT correlation, and this Oblivious linear evaluation correlations from LPN or variants of that. But although I'm going to talk about it, all of that was a starting point we had when we started the work. I want to mainly talk about here. So the main thing we wanted to look at in this work is the following question. Everything we know how to do, even taking into account all our past works, which I'm going to tell more about, were pseudorandom correlation generators, which were limited to a one-time stretch of a fixed bounded polynomially long pseudorandom correlation. So you take your seed, you expand it, you get a big chunk, say 1 million Oblivious transfers, and you have to store all of them, and you cannot get more, and you can now start doing secure computation with these Oblivious transfers. However, the dream result for secure computation will be something which is much more incremental and reusable. The dream result will be that from your seed, you can how many times you can indefinitely say stretch the next Oblivious transfer you want, if we focus on this target correlation, for an indefinite number of time. So Alice and Bob would interact once, generate seeds, seed A and seed B, and whenever they need some number n of Oblivious transfer, they will retrieve the seed, stretch n Oblivious transfer from it, and keep the seed ready for later use. So, yes?
The question, so are you, maybe you'll tell us like more about like where previous approaches why previous approaches like fail here, but is it because they changed the type of the, like why are they one time? Is that because they changed the type of the randomness, or something about security parameters that decreasing quickly, or?
So the big reason is that the way these LPN-based approaches worked was by first generating a long string and then multiplying this long string by a very large public matrix. Okay, so this string was of fixed bounded size, and then you multiply it by a very large public matrix. And the problem is that if you want this to be practical, then you had to do this matrix vector multiplication all at once, because you can choose the matrix in a way that the matrix vector multiplication is efficient, but it doesn't mean that you can one by one sample the coordinates that you want efficiently. I don't know if this is clear.
But like, I guess what I was wondering is why can't you do like the standard doubling trick here, where you sort of.
So that's a good question.
Double the number of pairs and then repeat, or like use half of them and
like a GGM tree, you mean?
Yes.
Or forget even the GGM tree, the simpler version even than that.
Yes. But, so this works. It has several downsides storage-wise. So essentially, each time you need to sample to stretch a very big chunk, and the next chunk you will have to stretch will have to be twice bigger than the previous one once you've consumed all of this one. But if you use a doubling trick, at some point, you will have, each time you want one next OT, to stretch a very large number of OT and store them all. Does that make sense? So that removes the upper bound. Of course, you can go to an exponential upper bound by using the the doubling trick if you have an exponential compression in the seed size. But this comes at the cost of having to stretch many OTs at once each time you want to generate one, as soon as you've as soon as you've already used a lot of them.
So you're saying that your memory is going to be proportional to how many pairs you already generated so far?
Yes.
Okay.
Yeah, I guess I'm not sure I see why that is, but it's fine. You know.
Yeah.
You'll tell us what we need to know as.
Yes. It should become clear what is the limitation of the previous construction, because I will present them. So it's not impossible that this doubling trick works. So let's just formulate it as it's unsatisfying as a generic solution because of storage issues, and because you cannot really stretch the OTs one by one, but you have to stretch them by big chunks. So this will become clear. So
as far as I understand, it's really more like a concern of like efficiency of like the stretch rather than like actually a reusability, right? Like you can actually like stretch for like as much correlation as you want with prior X. It's just that you have to like stretch, like get all the correlations at once or something like that, right? Is that the difference?
Yes, that's the main difference. Now what we want is I have no a priori upper bound on how much randomness I'm going to need. And each time I want one OT, I can generate one OT. And the cost of generating one OT should be some constant, independent of the total amount that I've generated so far and that I'm going to generate in the future. Efficiency would be the dream solution.
But just to clarify, for previous work, there's no upper bound on the amount of correlated randomness you'll generate either, right?
If you use the doubling trick that Adam mentioned, no, there is no. There is no.
So it's mostly about efficiency in that, from this.
Exactly.
Okay, cool. Thanks.
So intuitively, you can also view it as a natural next step. Like we had the pseudorandom correlation generators, and we asked, can we have a pseudorandom correlation function? So now the seed is a key, and each time you want one pseudorandom sample of the correlation, you can locally compute it, and that's independent of how many you have generated in the past, or how many you're going to generate in the future. So how do we do that? So a correlated pseudorandom function, intuitively, that's a way to generate two keys, such that Alice and Bob get correlated functions with the following security properties. First, if you have black box access to samples of the form f of x with key ka and f of x with key kb, then those look like random samples from the target correlation. For example, random oblivious transfers. And the same improved security guarantee that we need is also that from the viewpoint of Alice, each evaluation on X with the key of Bob is indistinguishable from something that will have been sampled at random, conditioned on satisfying the correlation with the value that Alice can compute with her own key, and same condition in the other direction. So the possibility of doing that turns out to be related to a seemingly very different question, which is the question of building pseudorandom functions, and specifically weak pseudorandom functions, in low complexity classes. I'm going to say more about that. So what's a weak pseudorandom function? It's a pseudorandom function which is only indistinguishable from a random function when it's evaluated on uniformly random inputs. And a big, very interesting question in the area of weak pseudorandom functions, and also in the area of many, say, symmetric cryptographic primitives, is the question of what is the smallest complexity class in which such a function can possibly exist, or to use the terminology that Yuval typically uses, how low can we hope to go? This question is actually at the intersection of many quite interesting areas. If you can have a weak pseudorandom function in a very low complexity class, it's interesting for low-end cryptography. Typically, you can get symmetric primitives that can be implemented with very good parallel efficiency. But it's also very interesting for learning theory. So learning theory is the study of which function can be learned efficiently through black box access to their input-output behavior. And if a complexity class contains a weak pseudorandom function, then it's equivalent to saying that this class cannot be learned under the uniform distribution. So it gives a negative result in the study of learning theory. It provides a limitation for this field. And the third interesting point is that the existence of low complexity symmetric objects has been related in many works to the existence of high-hand cryptography. So for example, if we have constant locality pseudorandom generators, then we can do constant override secure computation. But also they have been instrumental in the latest construction of indistinguishability obfuscations and so on. And here again, it will be one of these kind of relations where we show that if we have a low complexity weak pseudorandom function, then we can use it to build correlated pseudorandom functions if they are in a sufficiently low complexity class. So before I explain what are the kind of complexity class we care about, let me tell you a bit more about the relation between pseudorandom correlation functions and low complexity weak pseudorandom functions. What we show is the following. If you have a cryptographic primitive known as function secret sharing for some complexity class, so what is function secret sharing? It's simply secret sharing for a function. So it takes as input a function, shares it into two keys, such that each key hides the function, so it does not leak which function from the class was used. But for any input, any share allows to locally evaluate the function and get a share of the output. And then if you evaluate your share of the function on the input x, and you sum the two shares obtained this way, then you reconstruct the output of the function. So if we have function secret sharing for some complexity class C, and that this complexity class contains a weak pseudorandom function, then we can build a pseudorandom correlation generators for the Oblivious transfer correlation. And if the complexity class is a bit more complex than that, it also contains products of the class C, which contains a weak pseudorandom function, then we can go even beyond that. This suggests two natural ways to instantiate a framework. The high-hand way is just, well, use the fact that we can do function secret sharing for all circuits. We know how to do that using, say, multi-key fully homomorphic encryption. So LWE style fully homomorphic cryptography. And if you use that together with any weak pseudorandom function, which you can implement over in P/poly, then you do obtain a construction of pseudorandom correlation function, but it has many limitations. So there is some imperfect correctness, which is maybe a technicality, but also it requires very powerful FHE style assumptions, and it's very unlikely to lead to concretely efficient candidates. So we decided to look at the other end of the spectrum, and the other end of the spectrum is, what if we start from the most efficient function secret sharing schemes we know of? So we know of extremely efficient function secret sharing schemes that only requires the existence of an arbitrary pseudorandom generator. And you can implement them with AES, and they are like extremely efficient, really. But they are only for very weak function classes. Especially, you can think of the functions captured by this function secret sharing scheme as being the sum of point functions, where a point function is 0 everywhere, except at a single position where it takes a specific value. So we can build function secret sharing from one-way functions for the class of sums of point functions, and it's extremely efficient. Does this class contain a weak pseudorandom function? And so this is one of the things I'm going to try to answer in this talk, and we're going to build naturally a weak pseudorandom function, which is in this very low complexity class, which is sums of point functions. So the way I'm going to present it will be without going through function secret sharing, because it will take too much time to keep introducing more and more cryptographic primitives. but I'll try to present really a natural step-by-step construction of pseudorandom correlation function for oblivious transfers, from which this new weak pseudorandom function candidate emerges naturally. And the construction will not use FSS because in the specific case we care about in this talk, the case of oblivious transfer, we only need a puncturable pseudorandom function, which is a much simpler object. Okay, so before I start with the construction, what do we know about low complexity weak pseudorandom functions? Because perhaps we already know of weak pseudorandom function in this class, so we could already use that. So if we care only about, say, cryptographic primitive with super polynomial security, then we have very good answers to this kind of questions, to the question about the complexity of weak pseudorandom functions. Of course, DGM gives us a PRF, so a strong pseudorandom function that can be implemented in polynomial time, assuming any one-way function. But actually, if we are happy with standard cryptographic assumptions such as DDH or factoring, we even have such pseudorandom function in the class AC0 of constant depth circuit with AND and OR gates of arbitrary fan-in. And if you are okay with slightly more exotic assumptions, such as the existence of random local functions, or even if you are okay with heuristic construction, then we even have candidates with very low depths inside AC0. So intuitively in the superpolynomial regime, the question of finding out what's the complexity of weak pseudorandom function is mostly settled. However, if we insist now on not having just some superpolynomial stretch, if we think that this is not sufficient for cryptography, then the picture becomes much less clear. First, a classical result from lineal Mansour.
Sorry. What's the difference between the last slide and this slide? I missed it.
Yeah. So the last slide says we only require super polynomial security of the primitive. Now we require that it can achieve subexponential security. And the main
is subexponential security, you mentioned the word stretch before. So are you talking about the assumption or the stretch or the size of the input to PRF?
Yeah, so I'm talking about say the stretch or the domain, the size of the domain of the pseudorandom function, and also the strength of the adversary. So the adversary has access to a subexponential number of samples and can run in subexponential time.
I see. So you lump them together. It doesn't need to be tied together, right?
Yeah.
Three different parameters, right?
They are two completely different things. We tie them together here for simplicity. But essentially, if you only care about superpolynomial security, I mean, there is one bound the other. I mean, if the adversary only has superpolynomial strengths, then he cannot even see more than the superpolynomial number of samples to start with. So there is no point in giving him more. But
also a connection by way of like complexity leveraging, right?
Exactly. So
the distinguishing probability, right, is there too. But the number of points that the adversary sees is different than the number of points in the domain of the function, right?
Yeah, sorry, I meant the number of points that the adversary sees.
Not the domain of the function. I see.
Yeah, no, the number of queries and the number and the running time of the adversary. But in the superpolynomial regime, the way this is achieved is you take some complex primitive with exponential strengths and you scale everything down. And then you get something in a much lower complexity class. And that's how you get things in AC0. So the DDH construction is just a now wrangled pseudorandom function scaled down.
So what do you mean scale down? Again, what do you scale down?
The security parameter. So you assume that you only take security parameter, say log square of lambda instead of lambda, and then you can squeeze everything into AC0. So you want circuits of size polynomial in lambda, and but you will take the now wrangled construction and you will scale, say, the size of the group to being only super polynomial. And you will assume that DDH is still secure if the group is just of slightly super polynomial size. And now you can implement the operations needed for this pseudorandom function in AC0.
Sorry, so what's, yeah, I'm confused. So normal Noah-Reingold is just an NC1, right?
Yes.
We're thinking about Noah-Reingold over like n-bit inputs.
Yes.
Right. So yeah, what are you doing in EC0? I actually now that you said it, I realize I'm confused too.
So I never worked out myself the construction, but from my vague recollection, the trick is just a scaling down. Like you take the group in which you do Noah-Reingold to be only of super polynomial size. And now the operations which...
So instead of taking n-bit inputs, you're taking like a little omega of log n bits.
I think it's uncorrelated to the input. It's only correlated to the function itself.
To the whatever the group size, that's right.
The group size, yes.
Okay. Okay, never mind. But say this is anyway, it's previous work, it's not your work. So
yes.
No, it's, yeah.
Yeah, so that's the state of the work, which lets us say that in the super polynomial strength regime, things are basically settled for the reason that you can scale down more complex construction from high complexity classes to low complexity classes.
And what do you give up when you do that? You give up strong PRF for weak PRF. That's the trade-off.
You give up subexponential strengths. I mean, you just end up with some.
Okay.
Yeah. If you insist on having subexponential strengths now, so not to use some complexity leveraging or like rescaling of the security parameters, then AC0 is out of question. So there is this classical statistical query learning algorithm that can learn all of AC0 in quasi-polynomial time. So you still have the GGM construction, you still have DDH factoring and LWE-based construction. Now they are in TC0, so slightly below NC1. And the question is, where does the truth lie? So what about in between? In ACC0, so where you can have gates that it's constant depth circuits where you can do some modular gates for any number. Then there was a heuristic construction 2 years ago. So it's not broken, it looks fine, but it's heuristic. And the big question is, well, this space between AC0 and ACC0, typically AC0, where you allow parity gates. And this has been studied for quite some time. There was a heuristic construction by Akavia et al., which was very nice and very cute construction with very elegant ideas, but unfortunately it was broken 2 years later by Bogdanov and Rosen. So that's pretty much where we were before starting our work. And so intuitively what we achieve in this work is a candidate weak pseudorandom function for the class of XOR normal form formulas. So what is an XOR normal form formula? It's you have one layer of ends followed by a single high fan-in XOR. And the layer of n also, they have arbitrary fan-in. So you take your input, you do a bunch of ends in parallel, and then you XOR everything. That's the class of XOR normal form. And so it's somehow as close as possible to AC0. It's depth 2 circuit, and it contains a single parity gate. Okay. So yeah, so this class, it looks like that. And intuitively, the concrete structure of our weak pseudorandom function is as follows. You take the input, the circuit is fixed. It tells you for each subset of the bits which ends to compute. And then you have to XOR everything. And the key only tells you which of the input bits to negate. So in itself, it's a very interesting candidate. Independently of the pseudorandom correlation function application, I find it quite interesting to have that we possibly have a weak pseudorandom function with such a simple structure, like just one layer of ends, then an XOR. And now we conjecture that it's still a weak PRF up to subexponentially many samples with respect to subexponential size adversary. And it's for me, it's an intriguing open problem to try to attack this candidate or find a counterexample.
So what is the key here? The key is the ends, the sets of the ends. So
the key is just a list. It tells you for each input whether you negate it or not.
Oh, I see. You just said it. I'm sorry. Yeah. Okay.
And so you view this as the inputs are literal, so they can be inputs or the negation, and then the circuit itself is entirely fixed.
So it's like a pad, a one-time pad, well, not one time, but like a pad for the input.
Yeah,
right?
yeah, exactly. It's just an XOR.
You XOR k into the input. It's like f of x is this thing applied to x plus k.
Exactly.
And what's the structure of the AND gates? How do you decide which inputs get ANDed together? So that's not part of the key, that's part of the initial setup.
That's fixed.
So how is that decided?
Yeah, so it's fixed. I will give it the exact construction, but basically you break the input into many parts, and then so they will not intersect. It's like we will really apply the AND to independent parts of the inputs, and we will have a bunch of all possible fan-ins. So we will have, say, security parameters fan-in 2 AND gates, then security parameter fan-in 3 AND gates applied to a different parts of the input, and so on, until some like number which is also related to a security parameter. So really we cover all possible fan-ins on independent parts of the inputs. Okay. Okay, so I'll try to do a quick walkthrough to explain.
Actually, just to finish this slide, the previous slide. So we're talking about building a PRF.
A weak PRF.
Is just generating 1 bit enough here, or is that?
Yeah, it's generating 1 bit at a time.
Like that's sufficient. Like it's not obvious to me that in these low complexity classes, the sort of like, you don't have to worry about how many bits of output, like producing more bits of output is easy.
Oh, so parallel evaluations cost us nothing. So if you want you can do the trivial parallel extension of you concatenate independent parts of the inputs, and then you evaluate the function with independent keys, and then you get the number of bits that you want. And then that doesn't change the class to do all of that in parallel.
I see. And so in particular, that's like having the input be way longer is like fine here. That doesn't.
Yes. Yeah, of course we pay a lot on that. Like the input will be of size, say quadratic or even cubic in the security parameter for producing a single bit of output.
Yeah. All right, thanks.
And are you going back to the construction, or that's all we're going to see on the construction?
I'm going to explain how we arrive at this construction, if time permits.
Okay, great. So I'll shut up and wait for the explanation. Okay, thanks. Yeah. Okay.
So what we wanted to do was building a pseudorandom correlation function. And as I promised, I will first explain how we built in the past pseudorandom correlation generators, and then why this was not satisfying enough for us, and then how we go from that to pseudorandom correlation function, and how this weak pseudorandom function emerges from these steps of constructions. So let's start with the easiest, pseudorandom correlation generator. Quick reminder, we want to be able to generate 2 short correlated seeds that can be expanded into an oblivious transfer correlation, meaning we want that Alice and Bob get 2 additive shares, WA and WB, of the component-wise end of the vectors U and V. So this is an OT correlation. I mean, this is n OT correlations. And we construct this from the learning parity with noise assumption. The construction works in 2 main steps. I mean, so first, we reduce this question to the same problem, but for a simpler correlation. We reduce this to the question of building what we call the subfield vector OLE correlation, where now Alice and Bob, they want the same kind of output, so shares of u times x. But now x is not like the vector v. It's just a simple field element. So we want Alice and Bob to have additive shares of some field element x times a vector u. And we call that subfield vectorially because we want u to be still a vector of bits, so over f2. But now WA, WB, and X will be over some extension field of F2. And if we have that, then we can locally transform this into many pseudorandom oblivious transfer. And this is the classical IK and P construction for oblivious transfer extension. So intuitively, you take inputs of the form X and W minus X, and you hash them, which decorrelates them and which gives you many instances of pseudorandom oblivious transfers. So that's a well-known transformation from this correlation to the more complex correlation we care about. So now our target is to build this simpler thing. Alice and Bob wants to have short seeds from which they can stretch shares of x times u, where Bob knows x and Alice knows u. And we're going to do that in 3 steps. First, we will do it in the very simple case where u is just a random unit vector. So it's very, very long, but it's 0 everywhere except at a single position where it's equal to 1. Then we will go from a random unit vector to a random sparse vector by just repeating the construction many times in parallel. And then we will show how to transform this construction where u is a sparse vector into a construction where u is a pseudorandom vector. And this is where LPN will play a role to transform some sparse thing, which we'll view as some noise, into some pseudorandom string. Okay? So first step, we want to generate seeds, seed A and seed B, of x times u, where x is known, say, to Alice here, u is known to Bob, but it's a random unit vector. The idea is just to use the classical GGM construction. So in the GGM construction, you start from some key k, and then you stretch it with a length doubling pseudorandom generator. So you obtain 2 keys, and each of them are stretched again and again until you get like all the possible outputs. This key k, we say, will be the compressed version of the share that Alice is supposed to get, this WA. And the expanded shares that Alice gets will just be all the leaves here. This will be this vector of length n. Okay? Now what we want Bob to get is some vector WB, such that if you XOR it with WA, you get something which is 0 everywhere, except at a single position where it should be equal to x. Well, if you're familiar with puncturable pseudorandom function, maybe you already see how to do it. Suppose that this is the position given by u. So this is the position where u is non-zero. We call it alpha. We look at the path from the key to alpha. And then we give to Bob the copath. So all the values in the copath in this tree. From the copath, Bob is able to compute the entire vector of leaves of the tree here, except at the position alpha. And so for the missing value, we just give to Bob this missing value XORed with the value x. And the size of this share now is only logarithmic in n. So Alice and Bob have shares which are of size at most logarithmic in n, from which they can stretch into additive shares of a vector which is 0 everywhere, except at the position known by Bob, where it's equal to the value x known by Alice. So that was for the first step. Now, and so yeah, the evaluation is the stretch is just you evaluate the entire GGM tree here, and same thing for Bob, plus inserting the missing value at the relevant position.
And this is essentially the FSS for point function, right?
Essentially, but FSS for point function is stronger because it also works when none of the parties is allowed to know the position of the point which is removed. But here for OT, it's okay that Bob knows this vector u. FSS works even if U is kept hidden from both parties.
Thanks.
Yeah. Next step, we want to go from random unit vectors to random t-sparse vectors. So vectors which have a random subset of t coordinates, which are 1 and which are 0 otherwise. Well, that's easy because everything is additive here. So we just repeat the same step t times. So with the same x always. So Bob gets these t unit vectors. We view u, the vector, as the sum of these t unit vectors. And these independent punctured keys plus the missing point. And doing the expansion is just doing the t expansion independently and XORing everything in the end. So then in the end, these expanded strings here just XOR to x times u, where u is a t-sparse vector. Very easy until here. And then what the question is, how can we go from here to the case where u is not sparse, but pseudorandom, which is what we need if we want oblivious transfers in the end, pseudorandom oblivious transfers. And here we use LPN. So what is LPN? It's the assumption that states that if I give you a system of equations, an overdetermined system of equations, so this is a big random matrix that gives you the list of equations. So here you have the list of equations, some short secret. And to this equation, we add some very sparse noise. So a small random subset of the equation is perturbated with a truly random noise. It's flipped at random. Then LPN tells you that it's infeasible to distinguish this perturbated overdetermined system of linear equation from a truly random string. Now, there is an equivalent version of the LPN assumption, which we call the Dual Lpn Assumption, which works as follows. You take the parity check matrix of G. I mean, a parity check matrix of G. It can have many such matrices. So a matrix of vectors in the kernel of G. If G is distributed as a random matrix, and H will be distributed as a random matrix as well. And you multiply everything here. Of course, it cancels the matrix G, as well as the short secret. So you end up with the following equivalent assumption. Given a random big compressive matrix H, if you multiply a very long sparse vector with this compressive matrix H, which is random but public, then the output looks truly random. And so this is equivalent to the learning parity with noise assumption. So the way we use that is just we take our construction where u is a t-sparse vector. So now from their seeds, the same as in the previous step, Alice and Bob can stretch this WA and WB who sum to x times u. And they just multiply their WA, U, and WB by this big public compressing matrix H. It's a big matrix, but it's public. So, and again, by linearity, what you get is just that those things are additive shares of x times H times U, which now under the LPN assumption is a pseudorandom vector. Okay. So wrapping up, we have now a technique where Alice and Bob can stretch seeds of size, say some security parameters times t, which is some LPN noise parameter, times log n, where n is the size of the vectors they want in the end. And from this, they can generate shares of this x times u. And using some correlation robust hash function and known techniques, they can locally convert that to n instances of a pseudorandom oblivious transfer. Now, the bad thing about this, the reason why it's hard to turn this into a pseudorandom correlation function, is that expanding the PCG boils down to first generating a long noise vector, so shares of this x times what will be the noise vector here, and multiplying that with a big public matrix. So intuitively, we're very limited if we want to be able to go to exponential size in terms of computation. Of course, you can use a length doubling trick, but then each time you like reach the limit of what you could do, and then you need to use the next seed, then you need to generate this super long vector and multiply it with this now twice bigger random matrix. So computationally, the computation keeps multiplying by 2 at each step. So kind of the dream result would be to get a pseudorandom correlation function to be able to have this matrix H exponentially big and to be able to compute each entry of the product H times the sparse vector, each entry in time, which will be, say, polylog in the dimension of H. So there we could just locally compute all the outputs we want one by one with some small amount of computation and for up to an exponential number of outputs. However, so the natural way to make this computation very efficient and independent of the dimensions of H would be to have H to be very sparse. But of course, if you take H to be exponentially big and extremely sparse, then you cannot hope for this product to be pseudorandom, sparse matrix times a very sparse vectors that give you a sparse vector. And if at the same time you make the matrix H dense enough such that when you multiply it with a sparse vector, the result is dense, then the matrix H cannot be big enough for our purpose. So to get the best of both worlds, the trick we use is to study what happens if we make the matrix H variable density. So now we look at a variant of LPN, which we call the variable density LPN assumption, where the matrix H is exponentially big and the noise vector is exponentially long. Then the first, say, 2t rows of the matrix, where t is some parameter, think of it as some security parameter, are very dense. Then each time you have a twice bigger block, but with the same number of ones per row. So the density is divided by a factor 2 each time. And this way you can have an exponentially big matrix, but which has a very succinct representation. You only need some polynomial amount to represent each row of the matrix H. And we take the exact same distribution for the noise vector. It's very dense at the beginning, then slightly sparser, then twice sparser, and so on. And really the way we do that is just each of these things here is broken into t blocks of size 2 to the I. And each block of size 2 to the I contains a single one per row. So you have exactly t times 2 to the I 1 per row of those big blocks. Sorry, t ones per rows of those big blocks, which are of length t times 2 to the I. So this is really the high-level naive idea about how to get the PCG construction to work if we want H to be exponentially big and to have the computation of any single output, so row times noise vector computation, to be of time independent of the dimension of everything, just something proportional to security parameter. So there are two things one might ask about that. First, what's the relation with this low complexity weak pseudorandom function I talked to you about? And second, is it secure? I will probably not have time to develop a lot the second part, but let's at least develop the relation with this weak pseudorandom function I discussed earlier.
I'm a bit confused. And how does the computation actually works here? I mean, so I understand the matrix is conceptually infinite, but you know, do you just work on prefixes of the matrix every time?
No, the matrix, sorry, it's fixed, but it's fixed at some fixed exponential bound. Okay. So polynomial time parties, I mean, yeah, we do have an upper bound, but it's exponential.
But I see, so the representation of the matrix is polynomial.
Yes.
Because it just represents the number of ones, right? The location of the ones, okay.
So what we only work with, the representation of one row of the matrix is polynomial. And we only work one row at a time because we view each correlation that we want as something which will be roughly a product between one row of the matrix and a sparse noise vector. And each of these rows has an efficient representation.
I see. And then how many rows do you work with? Or you say there's a polynomial number of rows?
We can work with up to 2 to the d rows, where d is some security parameter. So we can allow up to some exponential number of rows, but we sample the rows like along the way.
I see, okay.
So yeah, we've reviewed that as each time we need a new instance of the correlation, we sample a new row. It's easy. It has a polynomial representation. Then we multiply it with the same fixed long sparse vectors that we have. And this does not take computation proportional to the size, but only proportional to the security parameter. To some polynomial security parameter.
To the number of ones, in some sense. Okay.
Yeah.
Okay.
So what's the relation with this low complexity weak pseudorandom function I told you about? Well, if we develop this computation, here, what we're doing when we're computing this matrix vector multiplication is multiplying this block with this first block of the noise, and this block with this second block of the noise, and so on. So in the end, then we XOR everything. So we have an XOR from 1 to D, where D is some security parameter, which is a number of block. And we want 2 to the D to be like the limit on the max number of samples we can get. And then if we look inside of each block, as I told you, each block is broken into T subblocks. So, and the same thing for the noise vector, which has the same distribution as a row. So again, inside of that, we have an XOR of T subblocks with subvectors here. And if we zoom in, what happens when we multiply here, say one subblock, let me call it this vector HEJ. And we do the inner product with the corresponding subblock here, so EIJ. If we zoom in, as I told you, each of those is a unit vector because this is T unit vectors each time. And the inner product between two unit vectors, well, if I call xi the position of the one here and ki bar, the bar is just for notational simplicity. So the so this is yeah, I'll make it where all bits are flipped in K. Then this inner product between these two unit vectors, it's just an equality test between xi and this ki flipped. Another way of writing it is that this is just a big end between, or I forgot an L index here, but this is just a big end between the xijl XORed with kijl. Does that make sense? So an equality test is just you XOR the strings and you check that everything is equal to 1 in the XOR, or everything is equal to 0, sorry, in the XOR. Hence flipping all bits here for simplicity. So in the end, the candidate low complexity weak PRF is just the following. An input defines a row of this big matrix. And it's just a list of these xij's that tell you where is the one in each subblock. The key defines this noise vector, which will tell you essentially which of the inputs to flip. Each time you put, like you XOR here with some bit of the key, you're flipping the corresponding input bit. And then the weak pseudorandom function is just the multiplication of this inputs that defines this row of the big variable density matrix with the variable density noise, which is defined by the key, which can be expressed as just one big XOR of an end of the bits of the inputs flipped according to the key. Does that make sense? And the conjecture is that this candidate cannot be broken. Say if I call n the input size, and it's the same for the key size because key and input, they have the same size. My conjecture is that this is secure up to 2 to the cubic root of n samples against all adversaries running in time 2 to the cubic root of n. So subexponentially many samples and subexponential time adversaries. And I won't have time to explain a lot about how we give support to this conjecture, but we do give a lot of support to this conjecture. So how much time am I allowed to take? 10 minutes? Or...
Okay, sure. Yeah, I think if people want to leave, they can leave, but those who are interested. So maybe we can give a minute for people who want to go and ask high-level questions, they can ask, and then we can continue whoever wants to stay.
Yeah.
Yeah. Anybody?
Okay.
Feel free to continue. Yeah.
Yeah. So I won't give the full details, but the high-level intuition is the following. What we introduce is a new variant of LPN. So what we call variable density LPN. First things to do, looking at the literature about all published attacks on LPN. So, well, there is quite a number. Like I'm making a non-comprehensive list here of all the papers I could find about that. And it will be very cumbersome to go through all of them. But the very nice observation and the key to all this analysis is that all these attacks, they fit into the same framework, which I call the linear test framework. What is the linear test framework? It's I call linear test any attack that you can formulate as the following game between a challenger and the adversary. First, the challenger samples this random code matrix for LPN, and then the adversary is allowed to run in unbounded time. And after running in unbounded time, given this code matrix, it should produce what we call a test vector. And this test vector is whatever you want, just non-zero. This is just a trivial case we exclude. And then we say that the adversary wins if now when we sample the secret and the noise and compute the inner product between this test vector and these LPN samples, then the distribution we get is biased away from 0 or from 1. So what it says in more natural terms, more common terms, is that this captures all distinguishing attacks against LPN, where the adversary is allowed to, the attacker is allowed to depend arbitrarily on the matrix, but he can only compute a linear function of the samples. And the nice thing is that all non-attacks on LPN, say really information set decodings, the BKW attack, Gaussian elimination attacks, and all their variants, they can be formulated as linear attacks. So this also works if you look at the dual variant of LPN. So now the adversary gets this compressive matrix and is trying to attack this H times noise vector with the attack vector, and that's equivalent. So, and the nice thing is that we can prove that the variable density assumption cannot be broken by any attack that can be formulated as a linear test. So in particular, the entire literature of attacks against LPN cannot asymptotically break our new assumption. Why? Well, giving details will really take much more time.
I'm sorry, I'm sorry, but can you go back for a second about how you formulate the attack? So I'm trying to understand what is the restriction that the attack makes. You're saying that, so like in this case, the attacker, he has, H, and he has also, in principle, this H, this H prime, right? Which is either random or pseudorandom, this one. But yes. You're saying,
so it will compute a function to try to distinguish whether he's in the case where this is random or whether this is LPN sample, so H times some.
So you're saying this attack, just to make sure that I understand you correctly, in this game, the adversary doesn't ignore, say, the second half of the input. It doesn't even look at the H prime. He just takes H and then he generates these V's that and tries to see if he gets something biased or something. But it's someone has to relate to H prime, right?
Yeah. So another way of seeing it is that the adversary makes directly the computation of this V times these other samples, meaning that the adversary can compute some arbitrary function of H and H prime, but where the function is restricted to being linear in the H prime part.
I see. So you're saying the adversary has H and H prime, but the only thing that he's doing with H and H prime is multiplying them by both by these test vectors V and see if they can see discrepancy in the result.
I mean, the test vector V can depend arbitrarily on H, so it can be dependent on any function of the matrix H, but then this H prime will be multiplied, then it will only compute a linear function of this H prime parts, whereas the coefficient can depend in an arbitrary way on the matrix.
I see. So the V is computed only looking at H, and then it's applied to H prime.
Exactly.
I see. Okay.
If H prime was truly random and V is non-zero, then this distribution will be the random distribution. So we measure the winning probability of the adversary by the bias of this distribution when this is not truly random, but when this is LPN samples.
I see. Okay. Got it. Thank you.
And so what we managed to prove is the following. Essentially, we proved that the distribution for any possible attack vector V, the distribution of this big variable density matrix times the noise, V inner product with this thing, is non-biased, or the bias is exponentially small. More precisely, what we show is that each component plays a very specific role in preventing this attack. So for example, here you can write that as a sum of D components, and the component number I, well, if you do, what we show is that for any attack vector V with Hamming weight between 2 to the I minus 1 and 2 to the I, then the inner product between V and this HI times EI part has exponentially small bias. So intuitively, this variable density thing gives you an XOR of components where each component will allow you to avoid some all linear attacks of some specific weight. So you have a window of attacks you can avoid. And then when you XOR everything, then you get something that resists all linear attacks at the same time.
So you're saying that given an attack against this, you can actually reconstruct an attack again, a linear attack against one of those regimes, right?
Yeah, because essentially the bias of the XOR of independent distribution is at most the bias of the the minimal bias of any of the distribution.
Yeah. Okay.
So we show that, so it suffices to show that for each attack vector V, there is one of those components that leads to a small bias. And actually we look at the weight of the vector, and if the weight is between 2 to the I minus 1 and 2 to the I, then we show that the I's component will have exponentially small bias against any possible attack vector of this weight. And so explaining exactly the proof will really take some time, but there is a bunch of cool analysis where we show that all of this can be reformulated as a nice balls and beans analysis, where we reformulate the problem as you threw one random ball into one bin taken at random for T independent set of bins. You do that many times, where the number of times is the weight of the attack vector. And in the end, you count how many bins have not too many odd number of balls and not too many even number of balls. So we're like the number of bins with an even and odd number of balls is roughly like balanced. We call good a set of bins which satisfies this property. And we're happy if at least half of the bins are good, because then when we multiply with the noise vector, then essentially each of these good bins will contribute exponentially to the bias. So going in more details will really take some time, but the proof technique is quite interesting. You can read more in the paper. So when you formulate it as a game like that, we can apply some kind of strong concentration bound, which is an Azimuth style concentration bound for those of you who are familiar with a standard concentration inequality. So it's called, it's Mach diagram, it's bounded difference inequality. It gives us a very strong concentration bound on the bias of, on the probability of having sufficiently many good sets of bins. And this is so strong, this bound, that it can even withstand a union bound over all possible vectors of weight between 2 to the I minus 1 and 2 to the I. And so this suffices in the end to conclude that all possible vectors in this range of weight are, say, killed by our matrix, by this distribution. So yeah, this is really too rough of a sketch to really give a good intuition. But the conclusion is really that we can show that with some probability exponentially close to 1 over the random choice of the matrix H, the bias of the distribution we get with respect to any test vector V is negligible. Then there are many other kind of attacks we could look at. We also prove in the paper resistance against algebraic attacks, which were the one that were used to break the previous weak pseudorandom function candidate in AC0 with parity gates of Akavia et al. So here it follows from standard result that in our context, none of these algebraic attacks that try to express the output as some logically rational function can also break. So none of them can break our candidate as well. And there is a list of more attacks. So no AC0 attacker can break them, no low degree test. Like if we generalize the linear test framework to low degree polynomial test, we can also rule them out. The statistical query learning algorithms can also be ruled out, and standard linear cryptanalysis technique can also be ruled out. So really all attacks we could find from the literature and which we could formalize in some framework, we could prove that these attacks cannot hope to break variable density LPN asymptotically. And so now the big challenge is, well, can you think of a better attack that is not in this list? Can you think of a way to break this that does not fit in any of the frameworks that we rule out, and that will break the candidate using less than 2 to the cubic root of n times n sample, where n is the size of the input and the size of the key? Actually, we have a more, say, smaller input variant, which has the same security against the same attacks, but which just reuse some randomness from the input more efficiently. So then we can even get this bound down to 2 to the square root of n. And this is known to be tight. There is no learning algorithm that in time 2 to the square root of n can efficiently learn any thing in this complexity class that we're in. So yeah, and I will also be very happy if someone found a concrete attack, like some attack in, like say, I don't know, time less than 2 to the 80 steps, when you instantiate the candidate with t is 150 and d is 40. So yeah, this is for me a very interesting open area of research, trying to find attacks that could possibly break this variable density LPN assumption.
So potentially it could be could it be even stronger than LPN? I mean, it could be the case that it's not that any attack against traditional LPN would immediately generalize to this one, right?
Yeah, so it could theoretically be stronger than LPN. So for example, it has a very low noise, but we could not even show that it implies public key encryption. So in theory, it could even be weaker than, it could even be a mini crypt style assumption in theory, because we don't know how to build public encryption from this assumption. While with low noise LPN, you have the Aleknovich assumption, construction, sorry, not assumption. And, but I don't believe that it's weaker than LPN. Actually, we even formulate a conjecture in this regard in a more recent paper. But we don't know, and it's really an interesting question. Also, LPN can hope to get in some parameter regime security 2 to the n over log n, while this cannot hope to get more than 2 to the square root of n. So, in terms of, we cannot hope near exponential strengths here.
Okay.
Yeah, and I'm basically done. So there is a big list of applications of everything I told you. So with this variable density LPN, we get pseudorandom correlation function that gives us secure computation with very nice features. One-time indefinitely reusable short setup, where you can do a one-time interaction, and then anytime you need one new OT correlation between you and the other party, then you can just stretch it like with using this pseudorandom correlation function with like simple cost independent of everything else, and for as many times as you want. So really, it's like all the preprocessing of all the future MPC protocol you might want to do will be reduced to this one-time interaction and only local computation. And this has a bunch of applications to other zero knowledge and MPC-related problems like two-round secure computation, NISIX with preprocessing, homomorphic secret sharing, and the like.
So what do you mean by preprocessing NISIC? Is it like you take MPC in the head and preprocess it, or is this something else?
No, I mean NISIC, where there is a preprocessing phase that gives a proving key to the prover and a verification key to the verifier.
Oh, so designated verifier. Yeah. Okay.
Yeah. And the NISIC is as reusable soundness, so the prover can send as many proofs as he wants. It sees as many answers from the verifier as he wants, and soundness still holds if he sees the whether the proof were accepted or not. And then after a one-time phase, you can do an arbitrary number of proofs very efficiently.
I see.
Is it weaker than just than ISIX, or?
Yeah, it's weaker than just an ISIC because
No, what you get from PCF. I assume that what you get from PCF is like something, I don't know, like, is it just about implementing the setup of the designated prover verifier ISIX, or?
so it's a designated prover and designated verifier ISIC. That's the definition of a preprocessing ISIC.
But is it about implementing them? Like, what's the use of PCFs for that?
We have a construction of NISIC that uses PCF plus, but it's from previous papers where you replace the PCF via PCG. Essentially, if you have black box access to OTs, you can do NISICs by compiling them from some information theoretic, say linear proof style NISICs. You can compile them with obvious transfers. And then you can get, after this one-time preprocessing, an arbitrary number of obvious transfers between the prover and the verifier, basically.
Okay, thanks.
Yeah, and so among the other applications, there is the applications of this new weak pseudorandom function. So there are learning applications, which says that like this very simple class will already be subexponentially hard to learn. And in later work, we've also studied the class of sparse polynomials. But yeah, won't have time to tell you more about that. And another funny thing is that, as you've seen, this function is just you apply some fixed function to the XOR between the input and the key. So that means that you get also a natural candidate weak pseudorandom function which satisfy security against related key attack for the XOR relation. Simply because if you have access to, say, random sample x fk of x and x fk XORed with delta of x, where delta is some related key offset, then actually what you get is just the evaluation of the initial function on some with the offset applied to the input. And for random inputs, this is still randomly distributed. So it's also under the same assumption, you get natural candidates for, say, correlation robust hash function or XOR RKA secure pseudorandom generators and weak pseudorandom functions, and which in the past was only known, like say from multilinear maps or very complex cryptographic assumptions. So it's an independent but quite cool application. And that's it. Sorry for being so over limit. If you have additional questions, I'll be happy to answer them.
Thank you.
Thank you. That's great. Yeah.
Thank you.
Yeah. It's interesting. So regarding efficiency, like with concrete parameters, did you try to implement or think how it would look like with concrete parameters?
Yeah, so we're currently strongly looking into it, actually. So say you want, I don't know, to be able to generate a billion obvious transfers. So not an infinite number, but something which will be big enough for many purposes. Sorry, 1,000 billion. So something which will be more than what you're supposed to need in most practical scenario. Then it's like producing an output. Each obvious transfer can be produced probably in the order of milliseconds. So the parameters we'll take will be that this t parameter will be about 100. This d parameter will be about 40. So you need something like 4,000 independent instance of this GGM construction I told you.
Mm-hmm.
So big, but doable. Oh, and there is a way to compress that a lot, and we can reduce this by a factor of d. So we can get down to essentially 200 instances of this GGM construction I told you. So each party has 200 times these keys. So it's maybe a few megabytes, I don't know.
Yeah.
And generating each output is pretty efficient, say of the order of, yeah, maybe under a millisecond.
Okay, interesting.